So for the last couple of talks, I've been telling you just general results about trying to embed contact 3 manifolds into contact 5 manifolds. Of course, it'd be also interesting to consider the higher dimensional setting, but I don't have a whole lot to say there, so we restricted to that situation. What I'd like to do for this talk and also the talk tomorrow is now start to do the other part of our discussion from the first lecture that happened in dimension 3. Once you knew something about transverse knots, you use them to actually build contact manifolds. You use them to try to understand contact manifolds better. So right now, we'd like to try to use what we know now about embeddings of contact 3 manifolds into contact 5 manifolds to try to actually understand something about the construction of contact 5 manifolds. And again, the hope is that maybe these sorts of things generalize to higher dimensions as well, but at the moment, I don't know. So let's get started. As we've been doing all along, I'd like to start by stepping back into dimension 3 and reminding you kind of some results in dimension 3 and telling the story in such a way that we can hopefully generalize it to higher dimensions. In particular, if you remember in the first lecture, I mentioned the result of Lutz and Martinet that all homotopy class of plane field had a contact structure in them, and then this result of James Conway that you can actually construct every contact structure on a 3 manifold by some sort of transverse surgeries. So I'd like to prove that for you. And once I've done that, then we're going to go and try to mimic that proof in dimension 5 and see what we have to add and how things change as we go. All right. But before I do that, let me just remind you a few things about some Legendrian and transverse knots. I'm mainly doing the Legendrian story because it's probably more familiar to most people, so it's just to hopefully psychologically be comforting. But at least in dimension 3, it's not going to be essential for us, where in dimension 5, we are going to have to understand the Legendrian situation as well. Anyway, so I haven't said a whole lot about Legendrian knots, but a Legendrian knot, of course, is simply a knot in a contact 3 manifold that's always tangent to the contact, too many typos. Sorry, that's always tangent to the contact hyperplane. So that's supposed to be, of course, the contact hyperplane at the point. The canonical example of a Legendrian is simply this example here, S1 cross R2 with a contact structure given by that form. And it looks very familiar to one that we've seen before. So what happens is along the theta axis, so along the S1, the contact planes are all tangent to the S1, and they're all horizontal. And as you kind of move out along the y-axis, you'll start to do this kind of this left-handed twisting we talked about before. But clearly, in this model, the theta axis is a Legendrian knot, and we can look at a little standard neighborhood of the theta axis, and there's a very nice, very, very simple fact that any Legendrian has a neighborhood contactomorphic to n epsilon for some epsilon. And there's another nice little fact. Is there a question?
I'm not sure about the d theta minus y dx.
D theta minus y dx, yes. Oh, sorry. OK, so what do I mean here? I basically mean, sorry, dx minus y d theta. How about that? So more typos, mathos, whatever. Thank you. Yes, exactly. Yeah. In fact, the other thing isn't even really. OK, anyway, yes, that's what I mean. Thank you. OK, good. So any Legendrian knot has a neighborhood contactomorphic to the appropriate contact structure there. And there's another nice little fact that's a little bit harder to prove, but also not that hard. And that's that if you look at the neighborhoods for different epsilons, they're actually the same. They're not exactly the same, but for all practical purposes, you should think of them as the same. So a small neighborhood of a Legendrian knot and a bigger neighborhood of Legendrian knots, really, no different. So in particular, when you're trying to understand what's going on with the Legendrian knot, you really don't care what precise neighborhood you have, just one of these in epsilons. Well, of course, if you have a Legendrian knot, it's always tangent to the contact hyperplanes. So you got your knot here, and your contact planes are kind of wobbling back and forth as you go along. So of course, they give a framing to the knot. So we'll call that the contact framing. And if you, the first type of surgery operation I want to talk about is contact plus or minus 1 surgery on a Legendrian knot, which simply means take out the neighborhood of your Legendrian knot and glue back in a solid torus so that the meridian to this solid torus goes to basically the contact framing plus or minus 1, depending on whether you're doing the plus or minus 1 surgery. And if you recall, of course, when you glue in a solid torus, the topological type of the manifold is completely determined by where the meridian goes. So I've, for all practical purposes, told you precisely what the contact manifold is there. Oh, by the way, I should just mention I'm going to slip and call it Legendrian surgery many times, so I might as well tell you, -1 surgery, contact -1 surgery on a Legendrian knot is called Legendrian surgery. Okay. Well, the contact structure on this manifold, it turns out there's a unique contact structure that agrees with the contact structure on M away from the surgery torus, and on the surgery torus is tight. That uniquely specifies the contact structure for you. That basically follows from the classification of contact structures on solid tori, which was probably originally due to Kanda, but it's also in Honda and Giroux, and lots of other people have done it since in more or less the same way. Well, one nice thing about contact plus or minus 1 surgeons on Legendrian knots is this is actually a kind of a very robust construction. You can get every contact structure on every 3-manifold, closed 3-manifold, by plus or minus 1 contact surgery on a Legendrian link in S3. So any questions about Legendrian surgery? Great. All right, let's move to transverse surgery. This is what I really want to focus on during this talk, so let's do this carefully. I gave you a very rough description of it in the first talk, but let me be a little bit more precise this time. Since we're actually going to try to prove something, we should be precise. So if you look at S1 cross R2, and I hope I got the contact form right this time, but this is the contact form I wrote down in the first lecture, and it's basically the one that gives you a contact structure that's perpendicular to the S1 cross 0, so that kind of axis there. And then as you move out on any ray perpendicular to that S1, the contact planes are going to be tangent to that ray and start twisting, and they'll twist in a left-handed fashion infinitely often. Okay? And again, you can kind of really understand the contact plane just by drawing its trace on these tori, because we know the contact hyperplane, say, at that point is simply the tangent line to that line plus the radial direction and just the span of that, right? So that describes our contact structures. Well, I'm going to describe, I'm going to need to consider these tori, so I'm going to call them T sub s when the r coordinate equals s. And then n sub s is going to be the solid torus inside of here that T sub s bounds. Notice that the slope of the foliation induced by this contact structure, as you get very close to the x-axis, it's very close to infinity. By the way, contact geometers in the audience might be thinking, gee, this thing that gets close to the meridional slope should be 0. But I'm trying to convince everybody to change their ways and agree with topologists. Topologists forever have called the meridional slope the infinity slope. So basically, as you get very close to the x-axis, the slopes are very close to infinity. And as you move out, you start to go from, basically think of it as negative infinity through negative numbers, getting very close to 0, getting to 0 out at pi over 2, and then you flip over and get positive slopes, and they start decreasing down to negative infinity again, and you just do this over and over and over again. Well, also because I don't want to keep having to write things like tangent inverse of s to tell you what the slopes are, I'm just going to re-index my tori by the slope. Now, of course, that gives a little bit of ambiguity, but we all can figure out. You can talk about the first time you hit that slope or the next time or whatever. OK, so yeah, this is what happens. As you kind of move out your radii, as you go out, you start hitting the slopes, infinity, -1, 0, and so on. OK, so that's the picture. We should be really familiar with this because we're going to be using it over and over and over again. But let's move on. So what is transverse surgery? So given a transverse knot in M, the knot T always has a neighborhood that's diffeomorphic to n sub s for some s. So basically, this picture for tori very, very close to the S1 here is a local model for any transverse knot. But by the way, notice in this situation, for different s's, those neighborhoods are very, very, very different. Unlike in the Legendrian setting, where bigger neighborhoods and smaller neighborhoods, they were for all practical purposes the same. In the transverse setting, bigger and smaller neighborhoods are very, very different, and that's going to be a very important thing as you try to apply transverse surgery, and it's one of the reasons why people don't like transverse surgery and try to avoid it and use Legendrian surgeries, because in some sense, what you're allowed to do is a little bit easier to understand. But let's move on. So anyway, so you have your transverse knot in your neighborhood that's diffeomorphic to one of these n sub s's for some s, and take any rational number less than s. Okay, so remember, we're indexing our tori by slopes. So if your neighborhood, say, came all the way out to, I don't know, this very big negative slope, then we could take some s prime that's got a more negative slope in there. and you look at M minus that solid torus. So now I have a 3-manifold with torus boundary, and on the boundary, I see curves of slope minus, S prime. It turns out that you can actually collapse every leaf of that kind of induced foliation on the torus, and here's a picture of it, right? So here I've kind of gone all the way out to, it looks like slope 0, infinity, but anyway, you've got some slope here, and each one of these curves is going to get collapsed down to one point on this circle, right? Because you've got a circle's worth of circles. So as I collapse all the leaves, I get a circle, right? And if you do that, this region in here, this region from ns minus ns prime, so that's just a T2 cross interval, when I collapse some S1s here, this becomes a solid torus over here. So in effect, I've done a Dane surgery, right? I've removed the solid torus, and I've in effect put back in a solid torus whose meridian now is a slope S prime curve. Okay, so I've done S prime surgery topologically on the manifold. So it's easy to see, actually I just said that. It's easy to see that M prime is S prime surgery on the knot T. And the contact structure, it turns out that you've got a contact structure on M prime minus T prime just by restricting the contact structure you had before. And if you notice, this situation looks almost exactly like we were talking about this morning when we talked about branch covers. We had a contact structure that was defined in the complement of a branch locus, and we said that we could slightly perturb it and extend it over the branch locus. Well, the exact same sort of argument tells you you can extend this contact structure on the complement of the collapsed torus to a contact structure on the surgered manifold. So it's a fairly easy construction. It was first written down by Eugene Lehrman. He called them contact cuts. This is something you can do in all dimensions. It's a very nice general construction. And it's a very fun construction. I actually thought about putting a slide in to do it. It's not that hard to do, but for time's sake, I think we'll skip it. OK, good. So we call this contact manifold, this M prime C prime, we say it's obtained from MC by admissible transverse surgery on T. And I should point out that the first time this sort of surgery was explicitly written down was in a paper of Vincent Collin, and shortly thereafter, David Gay wrote it down in his thesis. They were completely independent of each other. I don't think either one of them knew about the other's work. So these are independently did this. But this was this sort of thing was more or less implicit in the work of Martinet and Lutz back in the 1970s. But they didn't really write out in these terms, make it quite this explicit. Anyway, one thing I'd really like to point out here, and I guess I actually pointed out, I don't have to laser it out, is that when you're trying to do these admissible surgeries, the allowable surgeries you can do are limited by how big of a neighborhood you can find. And again, a priori, when you just have a transverse knot, it's really not clear how big of a neighborhood you can get. So it's really not clear that range of surgeries. You know you can do sufficiently negative surgeries, but really pinning that down is a bit of a pain. It can be done in some cases, but it can be difficult. So that's one kind of disadvantage to this surgery, but we'll talk more about that later. OK, so that's admissible surgery. And of course, if you have admissible surgery, you figure that there must be something that's not admissible, so there must be inadmissible surgery. So let me talk about that. Oh, sorry. Let me make a few comments on admissible surgery first. So the first thing to observe that David Gay did, and John Baldwin and I kind of elaborated on this a little bit and gave an explicit proof. It was implicit in Gay's paper that basically any Legendrian surgery, so these -1 contact surgery on Legendrian knots, can be done, is essentially equivalent to an admissible transverse surgery. So if you love to do Legendrian surgeries, you might as well do transverse surgeries. You can do the same constructions. But actually, transverse surgeries are a little bit more general. So John and I could actually work out the following little more refined version of this theorem, that basically, suppose you have a neighborhood of your transverse knot so that the slope that you can get out to is somewhere between two integers. Well, it turns out that every admissible transverse surgery less than n can be done by a Legendrian surgery. So it's kind of the converse to that theorem, right? So we said here that all Legendrian surgeries can be done by transverse surgery. And here we're saying that the transverse surgeries can be done by Legendrian surgeries. But now, if you start to get slopes between n and s, the situation gets a little bit more complicated. Basically, there's infinitely many slopes between n and s that you can also achieve by Legendrian surgeries, by Legendrians that are inside of this neighborhood. But it turns out that there's also infinitely many surgeries, admissible transverse surgeries you can do between n and s that cannot be done by any Legendrian surgery, any sequence of Legendrian surgeries on a Legendrian contained in the original neighborhood of your transverse knot. Now, you might hope maybe there's some much more complicated Legendrian very, very far away from your transverse knot. That's kind of cheating. You wouldn't want to do that anyway, but you might hope to do that, and in some cases you can, but we actually have examples where you can't do even that. So there are admissible transverse surgeries that cannot be realized by any Legendrian surgeries whatsoever. So basically these two theorems together show you that in some sense these admissible transverse surgeries are much more general than Legendrian surgery. So if you're trying to construct things, that's a plus, right? You have more flexibility, you can do more things. But if you're trying to understand things, that might be a negative, because for instance, it's known that Legendrian surgeries preserve tightness. We like that. Actually, the way that we proved that there are slopes in here that can't be realized by any Legendrian surgeries is we actually proved that admissible transverse surgery does not preserve tightness in general. It does most of the time in many cases, but it doesn't always do so. Anyway, but again, if you're just trying to construct things, it's a much more flexible construction. That's right. So when I just say Legendrian surgery, it means -1 contact. If I want to say +1 contact, I'll say +1 contact. Yeah, good. That's right, that's right. So in our paper, we didn't actually make the statement that it couldn't be done by any Legendrian surgery on any Legendrian knots because we didn't know that Legendrian surgery preserved tightness, but now that we do, we know for sure that, that these surgeries couldn't be done anywhere in the manifolds. We already knew they couldn't be done locally near the transverse knot, but yeah. Okay, good. So let's move on. Like I said, since there's admissible surgeries, you would expect there to be inadmissible surgeries. And inadmissible, talking faster than I can actually talk. Okay, let's try again. Let's start over. So an inadmissible surgery on the transverse knot T is the following thing. So of course, T has our nice little neighborhood in sub S, like it always did. So now let me remove T from M. So I have this kind of picture. I've got M, I've got this is the region N sub S right here, except I've removed the knot. And remember, when you remove the knot, when you compactify, you can kind of think of those slopes as going all the way to infinity. So it has those meridional slopes there. Okay? Well, now I'm just going to take a T2 cross a half interval, and I'm going to put the contact structure that's always tangent to the interval direction, but is, again, rotating in my left-handed fashion infinitely often. I mean, we could write down the contact form. I'm sure everybody could probably do it by now. I won't do it, but hopefully everybody understands what it is. So just as you go out along a point-crossed ray, you're just tangent to the ray and twisting in a left-handed fashion infinitely often. And so that's the picture. And we just glue these things together. So now I've got a 3-manifold here where I've kind of glued on this kind of T2 cross infinity to the end of it, to the boundary of it. Well, now, suppose I want to do some surgery, say some surgery slope S. Well, there's going to be some T in here. There's going to be some T parameter in here where the T cross little t, boy, I realize as I'm saying it now, that was a bad choice for the parameter, T cross little t, but oh, anyway. I guess you shouldn't have capitalization make a difference when you're speaking, but anyway. So there's a little t in here such that big T cross little t has slope S on it. And I'm going to pick that little t such that it's the first time I come across that slope. Right? So it happens infinitely often, but I'm just going to pick the first time. Well, now if I just take this M minus S, where I've kind of glued it with this T2 cross this little interval now, I now have a compact 3-manifold with torus boundary, and the slope on the boundary is my S. And remember, when you're in that situation, we can collapse all those curves on the boundary, and we have effectively then done S surgery on M. So of course, this M prime is S surgery on M, and as before, there's a contact structure induced on it. And we say that this contact manifold is obtained from MC by inadmissible transverse surgery on T. So I'd like to just really point out, this is a really interesting fact here, and why it's kind of surprising that admissible surgery doesn't preserve tightness, because when you do admissible surgery, right, what did we do? We took out a region of twisting near the knot. We just took it out and then collapsed it. So in some sense, we're removing twisting, so it should be less twisted, not over twisted. Whereas when you do inadmissible surgery, you're taking out the knot and adding some twisting before you collapse down to get your meridian again. So inadmissible surgery kind of increases twisting, and admissible decreases twisting. Anyway, so James Conway kind of extended the work of John and myself to see that if you look at plus or minus 1 Legendrian surgeries and you look at admissible and inadmissible transverse surgeries, they're really the same thing. And by same, I mean you give me the sequence of Legendrian knots, there's an obvious sequence of transverse knots associated to them, locally associated to them, that I can do surgery on to realize that Legendrian surgery, and vice versa. So they're really, in a very strong sense, exactly the same. Okay? All right. Well, you put this together with the Ding-Geiges result, and you immediately have this result I gave you on the very first lecture, that any contact structure on a 3-manifold can be obtained by admissible or admissible and inadmissible transverse surgery on transverse knots, which I'll just abbreviate to say transverse surgeries. Okay? So this is a nice extension of the original kind of Lutz-Martinet stuff, saying you can get everything, not just some contact structures. So again, as I said, it follows immediately from this observation, but I would like to give you a different proof, because the proof I'm going to give you is what I'm going to try to mimic in higher dimensions. So how would you try to prove this result? Well, so suppose you're given your contact 3-manifold, so MC. I want to try to realize MC as transverse surgery on some link. So how am I going to do that? Well, the first thing I want to say is that M is obtained from S3 by surgery on some link. This is a well-known fact, but let me give you a proof of that fact. The first thing you prove is that any 3-manifold, or any oriented 3-manifold, is the boundary of some 4-manifold. And you might think, gee, the way I know how to prove that is I first prove this result, and then I observe that fact. But it's actually not so hard to prove. If you take any 3-manifold, it's easy, very, very easy to immerse it in R5. Once you've immersed it in R5, you can do various surgeries that can be undone by kind of adding handles to a 4-manifold to get to something that's embedded. When it's embedded, it bounds a 4-manifold. So I surgery the manifold to get to something that's embedded. The embedded thing bounds a 4-manifold because basically any hypersurface, any codimension 2 surface someplace, submanifold always bounds kind of a ciphered surface, or ciphered hypersurface. And then we kind of undo those surgeries to kind of get back to get the 4-manifold that the 3-manifold bounds. So you can prove this independent of knowing this result, that you have this 4-manifold here. So we start with our 4-manifold. Any 4-manifold has a handle body decomposition that has 0, 1, 2, and 3 handles. You don't need 4 handles because you have boundary, right? And you also only need 1 0 handle. Notice that the boundary of the union of the 0 and 1 handles is simply connected sum of S1 cross S2s. That's very easy if you've never done that before. Well, notice that if I add 2 handles with 0 framing on unknots, a bunch of those, I'll get some 4-manifold I'm calling x1 prime that also has boundary the connected sum of S1 cross S2s. So I can just replace x1 with x1 prime, and I have a new 4-manifold that has no 1 handles. And you can kind of flip this picture upside down and get rid of the 3 handles. So once you know you bound a 4-manifold, you actually know you bound a 4-manifold that just is obtained by attaching 2 handles. And it's super easy to see, if you've ever studied handle bodies, that attaching 2 handles is equivalent to doing surgeries on your knot. So that's the first fact we need, this purely topological fact that we can get from S3 to M by surgeries on a knot, a link, sorry, not a knot necessarily. OK, so step 2. Since there's no restrictions on the slope that I can do for inadmissible surgery, right? So you give me any slope on a knot, I can make it transverse and perform an inadmissible surgery to get to realize that slope. So starting with MC, I do all these surgeries that will get me to S3 through inadmissible surgeries. Now, in all likelihood, this C prime on S3 that I get is probably over-twisted, but who cares? Because it's a very, very simple exercise to see that you can get from the standard contact structure on S3 to any over-twisted structure on S3 by a sequence of Lutz twists, which are essentially kind of infinity surgery. So you remove a torus and glue back in the same torus without doing anything to the meridian, but you make the contact planes twist more. OK? Well, now you just have to observe that inadmissible surgeries undo admissible, and admissible undo inadmissible surgeries. So we can kind of reverse the process. So this first step, we just do step 3 to get from here to there. But now we reverse the surgery I did in step 2 to get from there to there. So I now have my sequence of transverse surgeries that gets me from S3 to anything. Okay? So that's the proof we want to try to mimic in higher dimensions. So before we move on, this is the simple version. So let's just pause and see if anybody has any questions. No? OK. Well, in that case, I'll have a little drink, and then we'll move on. OK. So we want to try to define these same sort of procedures, these same sort of surgery constructions in higher dimensions. So let's get started. So we want to do this in higher dimensions. So we want to actually try to prove that, that all contact 5 manifolds can be obtained by some sort of similar sorts of surgery operations. again, I think the outline of the proof you might try to do in higher dimensions, but there's definitely a few stumbling blocks that need to be overcome if you actually want to make it work. So we will just kind of stick to the 5-dimensional setting right now. So what is transverse surgery in higher dimensions? So first of all, I should mention this is a joint work with Conway. I'm only going to define the simplest possible version of transverse surgery because that's all we need. There is a more complicated version that really isn't technically a surgery in the sense of surgery theory or handle body theory, but it allows you to kind of build more general things. But we'll just stick with the actual surgeries. So what is transverse surgery on an S3? So we're going to assume that the S3 is contact embedded in my contact 5 manifold so that it's the standard, the standard contact structure on S3 is embedded in there. So in other words, when you intersect the tangent planes, you just get the standard structure. Okay? So that's the first assumption. The second assumption is we're going to assume that the normal bundle to S3 is trivial. So that is an assumption that's not automatic, but we're going to assume that. So those are the two things you need. And of course, you actually need this hypothesis to do surgery anyway, so it's not really a restriction. Well, under these two hypotheses, it's easy to see that there's a neighborhood of S3 that's just S3 cross D2 with contact structure given by this form right here, the standard contact structure, the contact form, sorry, on S3 plus R squared d theta from the D2 factor. Well, multiplying, yeah? The normal bundle to S3 in M5. Oh, actually, you're right. Sorry. Any D2 bundle on S3 is trivial. Great. So it's really not any extra assumption. But right. In general, though, when we look in other situations, I guess we do have to make that sort of assumption. But you're right. Here we don't. Here we don't. Well, anyway, so if you're away from R equals 0, then R squared is non-zero. So I can multiply by it. And you actually know that the kernel of that one form is not going to change. So away from R equals 0, instead of writing this form, I'm going to write that form. OK? Nothing wrong with that, right? OK, so let's move on. Well, notice, away from R equals 0, what I've got is S3 cross S1 cross some interval, right? That's what you got. And if you look at a form, a one form of the form, f of r alpha plus g of r theta, then as long as this condition is satisfied, so f is non-zero and this strange thing happens, so this whole thing becomes positive, then that's going to be a contact form. Okay? That's an easy little exercise. And this condition, you should think that if you look at the curve parameterized by f and g, the tangent to this curve is never radial. That's essentially what that condition means. So here's a curve that I'm going to parameterize by f and g, and it starts out with my f equals 1 over r squared and g equals 1, which is, of course, exactly what I had here, right? And it's going to end with f equals r and g equals minus 1. And I claim that this, so this picture gives me a contact form here. And if you look at this r alpha in this region, there's actually a symplectic structure on the 4-ball that near the boundary looks exactly like that. So what I can do is I can take my 5-manifold n, my 5-manifold m, remove the neighborhood, glue in this little region here that we just constructed through this contact form, and then glue in the B4 cross S1 with contact form, basically this kind of canonical one form on this thing cross minus d theta. But OK, that's fine. That's a contact form still. And that gives me a contact structure on this resulting manifold. And what have I done? I've removed S3 cross D2, and I've glued in B4 cross S1. That is exactly surgery on a 3-sphere. So I've performed surgery on a 3-sphere. I've got a new contact structure, and I'm going to call that the transverse surgery on the 3-sphere. Notice it was very important that the induced contact structure on my initial 3-sphere was the standard tight contact structure. If it was some over-twisted structure, I could not have done this trick. OK. And again, you should, well, not again, but I should mention that you should think of this as kind of being an inadmissible surgery, because I've added something to my manifolds. I've added some extra contact regions to my manifold to do the surgery. So you should think of the surgery on S3 as basically being inadmissible surgery, the analog of inadmissible surgery in dimension 3. You cannot have as much twisting as you want. It's very annoying. You can't keep twisting over and over and over again. You can only kind of flip past the vertical once, and you can never flip past the horizontal. So yeah, that's actually quite a limitation. But we're stuck with it. And by the way, somebody was asking me the other day, what about analogs in higher dimensions? It turns out that if you look at what we're doing, you can do the same thing for an S 2n plus 1, sorry, 2n minus 1 embedded in some 2n plus 1 manifold. You can do the same sort of thing. And you're also going to see that surgery on one manifold, S1s, are also OK. But everything in between, you can't play the same game. So you have some limitations on the sort of surgeries you can do. So anyway, it's annoying, but it has to do, part of this has to do with us just not knowing a lot about well, let me just stop there. I'm going to ramble more incoherently than usual, so it's probably best to just move on. Other questions? OK, great. All right, so what about transverse surgeries on an S1? Well, if you have an S1, well, we can certainly make it transverse to a contact structure. That's very easy to do, even in dimension 5. And it'll have a neighborhood that looks exactly like this. So this d theta plus lambda, where lambda is that, right? Away from 0, we can write it like this, right? Because we said before that this lambda, away from the origin, we can write it as r times the standard contact structure. So great. So we write it that way on the S1 cross interval cross S3. Again, we look at a contact form of this form, and we have this little bit here. Actually, what you have here is you just see it right here. You've got a 1 and an r kind of increasing as you go out. But I'm going to extend it by f and g that go like this. So the the g passes 0 here. So you can certainly do that. And I'm going to call this the standard contact structure on S1 cross D4. You might not think it's so standard, but I'm going to call it the standard one, at least the standard one. OK. So now what do we do? Well, given any S1, oh, sorry, we're still looking at the local model. Sorry. So I'm going to call n sub r just S1 cross the 4-ball of radius r in the thing I just constructed here. And let r naught be the place where where g is 0 and where f prime is 0. Okay. That's whatever the r, that's r naught right there. OK, good. So now, if you're given any S1 in some contact 5 manifolds with trivial normal bundle, again, I guess if it's oriented, they are trivial, but anyway. So it's going to have some neighborhood contactomorphic to this n sub r for some r. Assume that r is bigger than r naught. It might happen, it might not happen. Remember, if you're doing admissible surgeries, you can't always do surgeries you want. So you have to make an assumption. We're assuming we can get a neighborhood big enough. So assuming we have our neighborhood big enough, now remove that n sub r naught. And notice you've got the boundary of this resulting manifold is just S3 cross S1. And the S1 factors, if you look back here at this form, at r naught, this term is 0. So d theta, the tangents to the S1 direction, are in the contact hyperplanes. And this form is invariant under the action of kind of rotating in the theta direction, right? So under those two conditions, Eugene Lehrman's contact cutting says you can actually collapse those S1 directions and get an induced contact structure on the result. But when you collapse those S1 directions, what have you done? What you've done is you're essentially, in effect, kind of gluing in an S3 cross D2 here. So you've effectively done surgery on the S1 and put a contact structure on it. OK? So great. So we have a way of doing surgery on a transverse S1. And you should think of this as being very much like admissible surgery. Because remember, we had to make the assumption our neighborhood was big enough, and then we took something out and collapsed. So this is definitely the analog of admissible surgery in dimension 3. In any event, one important thing to note is that if you look back through those constructions, if you did surgery on an S3, the inadmissible surgery on the S3, you would have a neighborhood like this. And then you could do surgery on the resulting S1, and you would get back to the original contact manifold. And then vice versa, if you could do surgery on an S1, you would wind up getting a transverse S3 with a standard contact structure, and if you then did surgery on that, you'd get back to the original thing. The second one, yeah, the second operation is essentially, yeah. Yep. Okay, good. So those are my transverse surgeries. I'd like to say that's all I needed to build all contact 5 manifolds, but at the moment I can't say that. I think there might be a way of doing more general transverse surgeries and getting all contact 5 manifolds, but at the moment I need another surgery operation on 2 spheres. And to do surgery on 2 spheres, of course, well, they can't be contact submanifolds. So we're stuck with doing Legendrian surgeries. So what's Legendrian surgery on a embedded 2 sphere, or an embedded, say, n sphere? So suppose you have the round n sphere in Rn plus 1. And by that I mean you have the induced metric on the just kind of unit sphere in Euclidean space. Consider the unit cotangent disk bundle inside of the cotangent bundle, and consider its boundary, which I'll call the unit sphere bundle. You have what's called the geodesic flow on the unit cosphere bundle. Actually, really, if you think about it, what's the geodesic flow, right? If you look at a geodesic in your manifold and you take the derivative at a point, have all your geodesics parameterized by unit length. You take the derivative at a point, you'll get a point up in the unit tangent bundle, and as you move along that geodesic, you'll be kind of moving along in the cotangent the unit tangent direction. So you get this flow on the unit tangent bundle, and using your metric, you can actually identify the unit tangent bundle with the unit cotangent bundle, and that gives you a flow on the unit cotangent bundle. So induced by the geometry in your picture. So actually, we were, of course, hearing about that yesterday, but just saying a little bit more about it now. And notice that basically all your geodesics have period 2 pi, right? They're all circles. They're all great circles. And so that's what I need. I need the geodesic flow, and then I need one other thing. I need basically the antipodal map on a sphere, right? Any sphere has an antipodal map, right? It's at any point to its antipode. So given these 2 things, I can define the generalized Dane twist on the unit disk bundle, and it's just defined by this formula. So basically, you flow a certain amount depending on how far away from the origin you are, and then you apply the antipodal map. So I've just tried to draw the example here. Instead of going through the formula and talking through it so much, although you can stare at it, basically what I'm doing is the part here with all this F stuff, it's saying that at the 0 section, don't do anything. Basically, flow for time. If you're at the 0 section, the length of v is 0. So I'm flowing for time 0. So I don't do anything. I stay where I am. But when I get all the way to the boundary of the unit disk bundle, I'm going to flow for time pi, which means I flowed halfway around the sphere, right? Halfway around a geodesic. And in between, I'm flowing for less time, right? So this is the image of what happens if you do this for the S1 for this part of the map. And then when you apply d alpha, the derivative of the antipodal map, you get this picture. And that's, of course, the very familiar Dane twist picture in 2 dimensions. But this is a nice formula that gets it to work in all dimensions. And of course, notice that this Dane twist is the identity on the boundary of our unit disk bundle. So as long as you see this unit disk bundle sitting in any manifold, high-dimensional manifold, you can then extend tau to be the identity outside of there, and you have a well-defined diffeomorphism on your manifold, right? Okay, so that's a Dane twist, and we're going to use this Dane twist to define our Legendrian surgery on a sphere. So suppose you have a Legendrian sphere, Sn, in some contact manifold, 2n plus 1 dimensional manifold, of course. A regular neighborhood result tells you that there's a neighborhood of the sphere that looks exactly like a unit disk bundle cross interval inside of cotangent bundle cross R with the contact form dz minus that lambda. Remember that lambda is the one we talked about earlier. Oh, sorry, I just did that in Euclidean space. But the lambda is basically the Liouville form that kind of, it's the canonical one form on here whose derivative is the symplectic form on the cotangent bundle. Okay, good. So we know that our sphere has a neighborhood that looks like this. And now what I'm going to do is I'm going to remove that neighborhood from the manifold, and I'm going to glue back in the same thing by a diffeomorphism that's the identity on most of the boundary, but on the disk bundle cross upper epsilon, I'm going to apply this Dane twist, a plus or minus 1, the Dane twister, its inverse. And I'm going to call that basically the kind of plus or minus 1 surgery on the Legendrian knot. You need to check that that actually, kind of glues the contact structures together, so that takes a little computation, but it's not hard to do. So that's Legendrian surgery. Plus or minus, yeah? Yes, if you do the -1 Legendrian surgery, it's the same thing as attaching. If you take your contact manifold, cross with interval piece of selectization, add a handle, a Weinstein handle to the upper boundary, that's +1 surgery. Adding something to the lower boundary, that's essentially, sorry, that was -1 surgery. Adding it to the lower boundary to keep things, concave is the -1 surgery. So yeah, if you're familiar with that language, that's a better way to think about it. But this is, yeah. Okay, good. Other questions? Okay, so we have the pieces in place now. So let's now try to prove our result. Well, okay, and my notation, right? So you can do +or -1 Legendrian surgery through this process. And also, again, this is very important for me because remember in our proof in dimension 3, it's very important that as we did surgery operations, we could undo them with other surgery operations, right? So the +1 surgery undoes the -1 surgery and vice versa. Anyway, these surgeries, they really were implicit in the work of Eliashberg and Weinstein. They were explicitly said in Seidel, and then really explicitly studied more extensively, especially the +1 surgeries in Abdeck's work. And then we have this very nice result that we're going to need to make use of. Casals, Murphy, and Presses, when they were studying over-twisted structures, they give all sorts of different characterizations of over-twistedness in high dimensions. And one thing they proved is that if you do +1 surgery on loose knot, whatever that means, I'm not going to give the definition here. But anyway, there's lots of Legendrians that when I do +1 surgery on, I will get an over-twisted contact structure. Okay? So I will need that fact as well. Okay, so now I think we have all the pieces in place. So we want to prove now that any contact structure on any 5 manifold is obtained by transverse and Legendrian surgeries on the standard contact structure on S5. Okay? So let's see how to do that. Well, the first thing I want to do is over-twisted contact structures are nice. So I'm going to start with my manifold. I'm going to do +1 surgery on some Legendrian to get an over-twisted manifold. Okay? So that's the first thing I do. The next thing I want to do is notice that there's a 6 manifold X whose boundary is M prime. Okay? So that's not completely obvious, but it's actually true that in dimension 5, the cobordism group, the 5-dimensional cobordism group is trivial, oriented cobordism group is trivial, so they bound 6 manifolds. There's various ways to prove that. I won't bother to do that here, but let's just take it for a fact that, that my 5 manifold here bounds a 6 manifold. Well, our 6 manifold, of course, has no top dimensional handles. It has no 6 handles. But also the same argument I gave you before allows us to get rid of 1 handles and 5 handles. So we're left with 2, 3, and 4 handles. But what happens when you attach a 2 handle? You do a surgery on a S1. When I attach a 3 handle, I do surgery on an S2. When I attach a 4 handle, I do surgery on an S3. So basically, topologically, I can get from my manifold M prime to S5 by a sequence of surgeries on the S1, S2, and S3s. Okay? And in fact, I can do all the S1s first, then S2s, then S3s. That's not so important, but you can. Okay? So let's see how we're doing. Good. All right. So let me do those surgeries. So if I'm in my M prime with the contact structure C prime, I have some circles I want to surgery to get back to here. So I'm going to surgery on some S1s. Well, you can always make your S1s transverse. That's easy. If you want to, quote Gromov, but you can pretty much do it by hand if you want, so it's not that hard. You can also, when you realize these as transverse knots inside your 5 manifold, you can always assume the complement is over-twisted. That's also very easy to do. You just move your S1s away from the over-twisted region and do a C0 approximation so it stays away from your over-twisted region. Then I claim it's easy to get a sufficiently large neighborhood because of the over-twistedness of the complement. And the way you do this, I don't want to go through the details, but the way you do it is you just by hand construct what's called an almost contact structure that does what you want in the neighborhood. And then you apply the fact that any 2 over-twisted contact structures that are realize the same almost contact structure are actually the same, or isotopic. So we can certainly build this neighborhood because of the over-twistedness of our complement. And of course, once we do that, we can, once we do that, we can do the surgery on the S1, right? You can remove the neighborhoods, collapse the spheres, and you have your, you've done your surgery, you've done your surgeries on your S1s, okay? Good. Well, next step, do surgery on the S2s. Well, my 2 spheres, I'm always going to be able to approximate them by Legendrians. That's an easy thing to do. And I can arrange that the complements are still over-twisted. And now just do Legendrian surgery. No problem. Remember, there's no extra conditions to do Legendrian surgeries. Once you had your Legendrians, you could do your surgeries. So just do that. By the way, which surgeries do you do? +1, -1? It actually doesn't matter. Topologically, +1 surgeries and -1 surgeries on 2 spheres in S5 are the same. Now, in the contact world, they're not the same at all, but topologically, they're the same. So I don't care. Do either one. Do either one. Right, it's just basically because the Dane twist along a sphere, its square, is topologically isotopic to the identity, and that essentially says they're equivalent. Anyway, so do whatever surgeries you like there. And now finally we want to surgery our S3s. This is the hardest part. You have to work a little bit harder here. But what you do is, I've got an S3 I want to surgery on. Okay? So what I'm going to do is, I'm going to look at the complement of a neighborhood of that S3. And over here, I'm just going to have whatever contact structure I had, and I'm going to make sure that was over-twisted over here. So we can certainly do that. Now, in a smaller neighborhood of the S3, I'm just going to put whatever contact structure I want. So I'm going to put the one that is going to allow me to do the surgery I want to do. Okay? And in between, I just make sure I can extend the contact structures on these two pieces over this little region, which of course is just an S3 cross S1 cross interval, I guess. And it turns out there's no obstructions to extending the contact structure, an almost contact structure there. And then that allows you, again, through the Borman-Eliashberg-Murphy, to actually make that contact. And it turns out that actually, the way you've done this entire thing here is going to be isotopic to the contact structure you started with. So by using the over-twistedness of the complement again, I can actually just build the local model I want to use, so I can do so I have my nice standard neighborhood of a standard contact structure on the 3-sphere. So we do that, and of course, as soon as you have that, you can now do surgery on the 3 spheres. And of course, what happens? Well, you get the some contact structure then on S5, but that contact structure by construction is over-twisted, and I just make the really simple observation that you can do Legendrian surgery on some Legendrian in S5 with standard contact structure to get the over-twisted one. But now, since all the surgeries I've done are invertible surgeries, I can undo them by doing a corresponding surgery on an S1, an S2, or an S3. I can get from my standard contact structure on S5 to this over-twisted one on M prime. But then again, I undo this one to get back to this one. So I can get all the way back to my original contact structure. Okay. Sorry, when I say Legendrian surgery, I mean do surgery on a Legendrian sphere, not necessarily -1. So it's in fact, of course, it has to be a +1 Legendrian surgery. Yeah. Yeah. Sorry well, I guess I did say Legendrian surgery. I wasn't making a distinction in high dimensions between the two because I've been kind of, but yeah, you're right. It has to be a +1 Legendrian surgery on that sphere. But, yeah. What? No, but the point is, this thing is the standard sphere bounds a symplectic manifold, right? So we know it has to be a +1 surgery. Yeah. Okay, well, if there's no questions, I think I will stop there. Thank you. Yes. But actually, I don't think that's an essential feature. I think it actually wouldn't be all that hard. So if you go back through these steps, many of the steps I don't think are going to be that hard in higher dimensions. The real problem is there are certain surgeries in certain codimensions that we're just not really clear what's the nice geometric operation you're going to do there. But getting from a standard sphere to one of the over-twisted ones, at least in dimensions congruent to 1 mod 4, there's only a finite number. And I think just explicitly doing it by hand is probably not going to be very hard. In dimensions congruent to 3 mod 4, I think, I'm not so sure, because there I think you frequently do have, is it always? I think you always have infinitely many contact structures. And again, you can probably still prove that, but it would be, a little bit more challenging. Mm-hmm. So that's a good question. So in dimension 3, of course, where it's best known, Gay and Stipschitz have a nice paper about kind of attaching handles along a transverse curve. And they have this extra some extra homological condition in the complement of the knot to guarantee that you can actually kind of attach a symplectic handle along there and keep a convex boundary. So it can be done, but there's extra restrictions. And I've never quite understood really why they have to be there, but I've also never been able to convince myself that you can get around them either. But it seems to be more than large neighborhood. I thought it was just large neighborhood too, but they're conditioned on the one forms and the complement. As far as I can tell, don't seem to just be large neighborhoods. But maybe I didn't stare at it well enough. But maybe we should talk. If that's all it is, I'd be much happier. Because of course that's an obvious condition you need, and of course that means for integral surgeries, right? I mean, and also, of course, Eliashberg has this construction, when he kind of builds caps for manifolds, where he attaches along transverse curves. But there, he builds upstairs. He doesn't build a convex boundary. In fact, he kind of builds a flat boundary in some sense. It's a but then you have to know that you can perturb to get the convexity. But yeah, I mean the handles more or less look the same. Yeah. Yep. Right. 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 Yeah. Yeah. So right, there is some interpretation, and again, and then in this case, I actually think for the S3 surgery, I wouldn't be surprised if there is going to be some sort of symplectic analog of some sort or another. But of course, for the S1 surgery, since that's more like the inadmissible one, you really wouldn't expect there to be any chance of there being. Sorry, I said that backwards. So the S1 probably is okay. The S3 is probably not okay as far as like some symplectic operation. But I haven't thought enough about it to really see.